I'm happy to be here, part of your monthly group meetings. So first, I'm going to introduce some basic pillars of modern physics. There are three basic pillars. The first one is that forces and matter are both made of particles. So forces and matter are both made of particles. What does that mean? That means, for example, if you think about electron, which is a particle, and if two electrons are next to each other, they repel each other by electric field. But the repulsion of the electrical field is represented by exchanging a photon, where one electron sends a photon and the other one catches it. And in this way, they convey force between each other. So both the particle, in other words, the matter, and the forces, which in this case is electromagnetic force, are represented by particles, photons and electrons. So that's the first pillar of modern physics. The second one is quantum mechanics. Everything in the universe is governed by the laws of quantum mechanics, which basically says that when you go to the microscopic aspects, when you zoom in to the microscopic aspects of matter, you find that there is some fuzziness, and the particles are not exactly localized at some point, but they're kind of fuzzy like a cloud. And you can find particles in this cloud with some probability, and this leads to these kind of a probabilistic aspect of physics and the fuzziness of quantum mechanics. So at far away distance or macroscopically, everything looks precise and classically nice and so on. But if you zoom in, you have this kind of a fuzzy probabilistic universe, which is fundamental aspect of our universe. So that is the second aspect of the pillar of the universe. The third one is Einstein's theory of general relativity. This theory basically says that space and time, first of all, are unified into one object, and moreover, it's not kind of a like flat, but it can stretch and squeeze and so on. In other words, space and time are curved. So people often represent the curved space and time somewhat heuristically, cartoon-like, in this kind of picture. Like if you have matter like stars or sun or moon or whatnot, you find that the space near them is kind of, instead of being like straight, they kind of get curved. Of course, these are invisible grids that you cannot see with your naked eye, but if you can see it by, for example, by sending a light around, and the light doesn't go straight anymore and kind of bends as it goes around, and this bending is what's measured, what measures this curvature of space and time. So these are the three pillars of modern physics: forces and matter are particles, fuzziness of quantum mechanics, and Einstein's general relativity, which is applicable especially to large distances as well. In other words, when you talk about solar system scales or galactic scale, or even the whole size of the universe, these are nicely applicable. So Einstein's theory is very good and very powerful in describing the realm of big, large-scale physics. And quantum mechanics gets to be good in the short, tiny, microscopic features. And guess what? It turns out that all these three things cannot be all correct at the same time. If you assume 1, 2, and 3 are correct, you get inconsistencies, illogical results. So one of these three has to go. These three cannot be true all at the same time. And it turns out the thing that has to go is the first one. The first one, it turns out to be not true. Forces and matter are not made of particles, but actually are made of strings. Not point-like objects, but extended objects like one-dimensional strings, like loops. So what is string theory? Well, string theory is basically a theory which has been pursued for over 50 years now. And it was pursued when I was I think like 8 years old. So it had nothing to do with its creation, needless to say, but it has been around for about 50 years. And it is by now the most promising candidate for unification of Einstein's theory of gravity and quantum mechanics. So it brings together Einstein theory and quantum mechanics in a consistent way. And the basic idea is that you replace point-like objects like quarks, electrons, you name it, by strings. So what does that mean, you replace it? You replace it means this: if you take elementary particles like quark or electron, and if you imagine having, magnifying glass, a hugely powerful magnifying glass, and you zoom in, really zoom in by like, not just a little bit, a huge amount, namely, if you can resolve distance scales of the size of 10 to the minus 30 centimeters, you might find that this particle is actually not like a point, but actually spread around a loop, like a string. So from far away, a string or a loop looks like a point. But if you zoom in, you will see a structure. And that's what we mean by particles are replaced by string. In other words, particles are always strings, but from far away, they look like particles. So for example, if you look at nuclei made of quarks, and these strings interact with each other by strings coming together, coalescing to one string. So this the joining of the strings, and also the opposite process of splitting of the string, is the interaction of the strings. Moreover, different vibrational modes of the strings describe all the elementary particles. Electron is one mode, photon is another mode, graviton is yet another mode. So it unifies all the objects into one vibrating string. So it's very, very appealing philosophically that we have just one thing unifies all these would-be particles into this higher dimensional object, a string. And the interactions are very elegant. This diagram, you see these two strings joining together. If I just drew it together, it looks like a pair of pants. And this picture is called the pair of pants diagram. You see the things come and join and make a pair of pants. And so we say that the pair of pants diagram describes all the forces in the universe. Isn't that simple and elegant, in some sense, surprisingly simple? However, it's too early to present the final formulation of string theory. It's a very rich structure, and we are learning more and more about it as time goes on. Now, experiments, unfortunately, today can't help much. This is very unlike the rest of science, and usually in science, experiments lead the way. In the case of string theory, unfortunately, experiments are not going to be able to help us in the short run, because the size of a string is about a trillion times too small to be detected in any experimental setup today. The current energies that you see in the colliders are far too small to be able to probe the distance scales, these tiny strings. So you have to really, when you shoot two particles at each other, you have to get them to be very close to each other. And to do that, you need huge energies. And those energies that you need to probe the distance size of the string to see the fine structure of the particles to resolve a string is too high for us to be able to do in today's experimental setup. It turns out that even the incomplete knowledge we have of string theory today, nevertheless, conveys important new principles of physics. And that is what I want to convey today. What are these principles we have learned from this incomplete project? So it's kind of like, okay, let me just get a status report to you. That's what I'm doing. So I'll try to give some of these principles using examples. Perhaps one of the most important things we have learned in string theory is what we call duality. Duality is the statement that two very different looking physical systems can nevertheless be identical. So you see, if you see an apple, if you see an orange, they are not the same. So what do you say? These are different things. So what happened, to our surprise, is that in string theory, we thought you ended up with physical situations which were as different as apples and oranges. But somehow we learned that if you look at the apple the right way, it becomes the orange. And so this amazing transformation of one physical picture to another is what we call duality. Duality is a surprising equivalences of physical systems where they did not have any right to be equivalent, like oranges and apples. They're different things, but yet we see examples again and again of things which are so diverse and so different, you could not have imagined they are the same, yet they happen to be the same by looking at it the right way. So this picture here represents the following. So in these corners, parameters, this is what we call parameter space. So these are think about these as choices of parameters in your theory, like strengths of interactions or this and that. Each point here corresponds to a particular theory. So as you move around in this space and you go to different corners, different kinds of physics emerges. So in one corner, you get something like an apple. And then if you go from here to over here, gradually an apple gradually morphs to an orange to a pear, and so on. I'm just using metaphors for what I'm saying. Of course, I don't mean really apples and oranges, but what I mean is that the physical system gradually changes from one to the other in a way that you find it amazing. How could it possibly be the case? And this is the duality that we have discovered in physics. And these are the choices of background solutions in string theory, corresponding to the size of the space and the shape and the things like that. Okay, so that's the first one I wanted to say. So these corners are the corners where the description of the physics is very different from each other. I'm just giving you these names, numbers 1, 2, 3, 4, 5, 6. They look like totally different things, but they're actually the same. Actually, I want to give a better analogy, perhaps. It reminds me of this Escher drawing. You see, if you look at this beautiful drawing of Escher, you know, somebody asks you, what is this a drawing of? Somebody might say, you know, it's a drawing of the day, a sky, and also the blackbirds flying. And somebody who's looking at this corner says, no, it's the drawing of the night with the white birds flying to the right. And someone said, no, it's nothing to do with the birds or the sky. It has to do with the ground and the fields and so on, black and white fields. And somebody says this, somebody says that. So it's completely different answers depending on which corner you're describing. This is very much like that parameter space I was telling you about. But you see this black bird here gradually morphs to become the sky on the right. And this white bird here gradually morphs to become the sky here. So you could say, aha, there's this duality between the bird and the sky, even though there's a priori looks very different. But you see this gradually becomes the sky. Now, this is not just in terms of picture, but it's actually what happens in physics, that the objects gradually morph in a seamless way from one corner to another, just like a piece of art. It's amazing, it's remarkable. So it shocked physicists to discover this duality. And this is probably the most basic thing we have learned in string theory in the past 20, 30 years. And it has very different aspects and very different manifestations. So it's quite remarkable. By the way, I didn't say, but in case people have, of course, I will answer questions at the end of the lecture as well. But if people have urgent questions in the middle of the lecture, please feel free to unmute yourself and ask your question.
Okay, the morphing that you show us is basically a topological operation where we first thing that we learn in topology, which is counterintuitive, is morphing the sphere to a cup.
Yes.
Right. So when you describe your moving in the parameter space from corner to corner, that may be topologically based.
Yes. No, I understand what you mean. So there's what you are saying is a duality that mathematicians will call no change. If you ignore the distance structure, the sphere and a kind of a cup could be identical. But what happened in string theory is that you can find, for example, a three-handled cup or a three-handled surface is equivalent to a one-handled object, which look topologically distinct. That's the kind of thing we found. Things which were not supposed to be equivalent, that topologically are different. I'm coming to those.
Okay, thanks.
Yes, but this is a good question. So let me start with the basics of space, first of all. What are the kinds of things that there are in the space? Is the dimension of space 3 spatial directions and 1 temporal direction? That's the first question. The answer is no. We have learned that there must be extra dimensions. These extra dimensions, here I'm drawing all the three dimensions as like a long line here, as if it's one-dimensional. And these extra dimensions, I'm drawing like tiny compact spaces like circles, like tiny circles. So this I'm drawing it like a extra space. So the space might be like the cylinder. If the circumference of the cylinder is sufficiently small, you would think it's just like a line. But we have learned that there are actually other dimensions beyond 3. Okay, how many dimensions do we have if it's not 3? Is the dimension of space and time well defined? Can we say what it is? The answer turns out to be surprisingly no. It depends on which corner of this duality we are on, what we call the duality frame. Duality frame refers to which corner of these parameter space you are on, right? Like the one corner where you got apple and the other one you got orange. So it depends on which corner you're at. You might start with one corner, the answer might be 10. If you gradually morph, you end up it's 11. And if you go somewhere else, it's like 12. And then you go somewhere else, it's like 9. So there's no well-defined answer to what the dimension of space and time is because of duality. It morphs from one to the other. You see, this is one example which is not topologically possible. You see, topologically, if the dimension is set, the dimension is the same. You cannot change it. But somehow in physics, the duality allows you to change the topological features. So it's not a topological invariant. For example, a 10-dimensional space could actually be coming from an 11-dimensional space in this way, or even much more bizarre way from other dimensions that there could be extra dimensions hiding behind. Like a line with an extra circle might be emerging. Or you could have, for example, a string, which is going from one side of a box to another, but actually it might be that it's talking about a membrane, but this because there's some extra dimension here hidden. Related to the question that was asked by Itamar, I think, is the topology of space a well-defined concept or not? Is that an invariant notion? Topology of a space is a mathematical invariant of a space, like how many holes or handles a space has. So one would think that it should be a duality invariant concept, that whoever says how many holes it has, they all agree. It turns out that the same physical system, the very same system, from different perspectives, can correspond to string theory, propagating the strings, propagating on spaces with different topologies. So they look like they're completely distinct. You can distinguish them using physics, using mathematics, but physically they're the same. That's a big surprise. So you can have a picture like this, which has 3 holes, and something which has 1 hole, and they could be equivalent, and we call them mirror pairs. That they somehow, the physics cannot distinguish between them, even though mathematicians thought that they are different. Is the diameter of a space? Can you measure the diameter of a space? It does that, or more specifically, is the diameter of a space a well-defined notion? For example, suppose you have a circle of circumference r, and if you send a light around here, it takes a while to go around and come back. If the speed of light is c, and the time it takes to go around is t, the total circumference r is c times t. So you might say, okay, so to measure this r, what you have to do is take a flashlight, send it around, and wait it to come back. And when it comes back, you measure how much time it took to go around. You multiply it by the speed of light, and you get the diameter of the space, right? This is the way Einstein would have defined the diameter of the space. It's a well-defined concept. It turns out that the diameter of space, or length more generally, is not an invariant concept. It turns out that the big space and the small space turn out to be equivalent, because in string theory, there's a symmetry which takes a circle of size r and says that's the same as a circle of size 1 over r. The big and the small, you can invert the length and they're identical. So here I'm using the units of strings. So in string units, if you take something which is 1/10 of the size of the string and something which is 10 times bigger, they are equivalent. It's very unintuitive. A huge box and an extremely small microscopic box behave the same way in string theory. This sounds like philosophical. If you read some of these philosophical things, they say big and small are equivalent. You say, yeah, all these philosophers. This is actually reality. In string theory, we actually understand precisely what this means. Small and large are equivalent. And how does that work? Well, you say that if I take a light and send it around, I measure what's the radius, well, how long it takes to come back, and gives you a measure of r. So how could it give you a different answer, 1 over r? It turns out that from the perspective of this other prescription, from this other framework, what appears to be a light is a different kind of a light. It's in fact not a light going around, but a wound string. And what appears to be light from our perspective is nothing but a wound string from the other's perspective. So it turns out that you exchange objects. What appears to be a light from one's perspective is it's not a light from the other guy's perspective, and vice versa. And if each one uses their own flashlight to measure the radius of the universe, they get different radii, the opposite of one another. So there's no well-defined notion to the size of the universe. This is remarkable. We might ask, okay, what are the black holes made of? Well, you throw something into a black hole, and you might think it's made of something, but when it goes inside the black hole, all the information of what's inside from where it came from disappears. Only you get the notion of how much mass and charge and spin there is, and there's no other notion that can distinguish black holes. So you lose all the information. So what are these? What's going on inside? What's happening to the things inside? It turns out that these mysterious objects that we have now taken pictures of, when you solve Einstein's equations, they tell you there must be black holes, and the spherical symmetric black holes in particular are solutions to Einstein's equation. And nevertheless, Hawking, following suggestions by Bekenstein, showed that due to quantum theory, black holes do not look like a single solution, but quantum mechanically, it picks up some degrees of freedom that we don't know how, but it turns out that these number of degrees of freedom should be huge and exponentially large in terms of the area of the black hole. In other words, if you chop the area of the black hole to tiny little pieces and measure how many of these tiny little Planck lengths fit in it, these tiny units of 10 to the minus 43 centimeters squares, and if you measure how many there are, this gives you the number of degrees of freedom inside that black hole, which is humongous. The area of the horizon of the black hole in Planck units, which is called holography, carries the information of what is inside. So from the area outside, you're discovering what's going on inside. So the main question from black hole perspective is, what are these states? Where are they hidden? And string theory answered this in an elegant way. And it says that black holes are like wrapped strings or membranes in the internal geometry. So if you have these, I told you there are these extra dimensions. So if you ask what are these, so if you have some string or some membranes wrapped around these guys, from the point of view of our universe, which is this blue space here, they look like a point particle. But if you wrap them more and more, it becomes very, very heavy, and eventually they form a black hole. And so therefore, you can count the degrees of freedom of the black hole here by counting how many ways you can wrap the string around this torus or donut-shaped object and whatnot. And this gives you the information about the degrees of freedom microscopic degrees of freedom of the black hole. Is that clear?
Now, once you mention the flashlight, I'm allowed to think about projections. And if I'm in the lower part of this slide, okay,
Yeah.
and I go with the right flashlight, you said people can have different flashlights and see different things, right?
Yes.
And
they're in different spaces too.
this is in the sense that if I'm using a different flashlight, I can move from one corner to another in the previous duality picture, or in this picture, I can move from the small to the big very easily, depending on how I direct my flashlight to get projection.
No. Let me explain that. Let me explain better. Forget about the right-hand column. Let's look at the left-hand column. So here,
Okay.
this yellow represents the flashlight, which is familiar flashlight. This,
Right.
in string theory, corresponds to a string which is very tiny, like a point particle, like a photon, which is point particle and it's going around. On the other hand, in the same theory, you can have a string which is wrapped around a circle, once, twice, 3 times, etc. This will not be a local flashlight. This is like this degree of freedom is spread all over the universe. So if you're living in this big universe, you usually use local flashlight, and the local flashlight is more made of like particles, photons in that case, which are localized at a point. Whereas if you wanted to use this other flashlight, you have to look at the whole universe together. So it's very hard for this guy to use this other flashlight. Whereas from the perspective of the other guy, it's exactly the opposite. What is yellow here corresponds to these wrapped strings around this, whereas this green thing, which is these winding strings, corresponds to the local flashlight of the other guy.
These are beautiful concepts that I have to absorb, but before that, there is something called projection and something called embedding. And if I play with these two operators, I can move from your left to the right.
No. You cannot go from left to right. These are two different spaces.
I mean, the two columns here, okay, I can find connections between them via using projections and embedding.
No. This is, so it's very hard to convey it, but let me try to again. This blue space and this yellow space are not in the same space. They're completely different pictures. It's not part of the same space. You cannot go from one to the other. I'm saying this blue space is equivalent to the yellow space. They're not two different spaces. They are the same space in a sense, but from different perspectives. In other words, one guy, the yellow flashlight sees it as this blue one, but this green light will see it like this yellow one. So different flashlights will give you totally different spaces. It's a very hard thing to explain, but this is precisely the beauty of duality. The duality tells you that what appears to one observer may be very different to what appears from the other observer for the same space. So it's quite remarkable. The thing is, it's amazing that all of these things are beyond what mathematicians would study. So it's not like simple geometrical operations like topology or geometry, like projections and all that. Those go down the tube. They don't help us. These conventional notions of geometry and mathematics are not adequate to describe string theory. We have to go beyond it, and these are examples of that kind.
Okay, thanks.
Well, so let me go back to the next question. Is the universe unique? Well, the word uni here somehow maybe refers to universe being unique, but actually the answer is a resolute no. By this, we mean that the number of allowed solutions that could represent our universe is far from unique. This is some things we call the number of vacua. That was one of the things that was mentioned at the beginning of my lecture by Betty. So what we call vacuum is this number of solutions to string equations. And so it turns out that the number of solutions are not unique, and there's a huge number of them. So string landscape is the number of such solutions, and there are too many to count. It's a huge number of them. Nevertheless, we have evidence that we live in an exceptional corner of the landscape. We're not at a typical point, maybe, it seems. It seems that exceptional forces and properties needed to explain the special features of particles that we have discovered. But nevertheless, this is a resolute no to the statement that the universe is unique.
Can I ask a quick question?
Yes?
Is that a reference to the multiverses?
Well, multiverses starts from one picture that the string theory is not unique in the sense that the string landscape, the solutions to string equations is many. So that's what some people call multiverse.
All right,
That's
thank
just
you.
this slide. Yes. Will the universe last forever? Well, we would have all hoped the answer is yes, but unfortunately the answer is definitely no. Well, I hope it lasts till the end of this talk at least. So let me finish.
Oh, no, you're not getting off that easily.
No. There are solutions to string equations that last forever. There are, I'm happy to say. But it turns out all of those that last forever, they enjoy a symmetry which we call supersymmetry that our universe lacks. So our universe is unfortunately not among those that could last forever. Okay, how long do we have? Well, we are not sure. There are different ideas about how long we have. So we cannot be really sure. And this is a little speculative what I'm going to tell you here. But there are some preliminary estimates that suggest that the time scale could be anywhere from now to 1 trillion years from now. So it's not too far in the future, like a factor of 10 to 100 more than the current age of the universe. So it's like we are like teenagers and we have 100 years to go. It's like that. So how would it end? We don't exactly know, but this is the kind of thing that could happen. You see, this is like galaxy, we're watching our sky and so on, and suddenly a bubble forms somewhere in a faraway galaxy somehow, and then it starts expanding with the speed of light and takes over everything. And that's the end of it. And that's the end of my talk as well. Thank you.